This scene deals with the subject many fathers find so difficult.
Welcome to Podcast VE 0.1, where we break down the latest research and tools for curious engineers. Alright engineers, let's talk Kubernetes. You've containerized your app, written your deployment manifests, maybe even tuned your resource requests and limits. You think your performance tuning journey is nearing its end, right? Well, maybe not. What if I told you that a core component of Kubernetes itself, something seemingly deep in the infrastructure layer, could be silently sabotaging your application's performance? A recent research paper titled Impact of etcd Deployment on Kubernetes, Istio, and Application Performance dives headfirst into this exact problem. The researchers Lars Larson, William Tarneberg, Christian Klein, Eric Elmroth, and Maria Kiel highlight something many of us experience but struggle to pinpoint: unexpected performance issues in complex systems like Kubernetes. The paper calls this emergent behavior, performance problems that aren't necessarily bugs in your application code, but rather arise unexpectedly from the complex interactions within the platform itself. The core argument of the paper is fascinating and crucial for anyone running applications at scale on Kubernetes. They propose that we often focus too narrowly on optimizing our application code and its direct dependencies, neglecting the profound impact of the underlying platform configuration. Kubernetes isn't just a passive container runner. Its own internal workings and performance characteristics directly influence how well our applications run. Think about it. Kubernetes is constantly orchestrating. It's scheduling pods, updating services, checking readiness probes, managing configuration changes, and maintaining the desired state of potentially thousands of containers across many nodes. All this coordination relies heavily on its central database, its brain, which is a distributed key value store called etcd. etcd holds the definitive state of the entire cluster. Every change, every status update, every configuration detail gets written to and read from etcd via the Kubernetes API server. Now, here's the kicker the researchers investigated. Where does etcd actually store its data? This might seem like a minor operational detail, but the paper shows it can have dramatic consequences. They tested two extreme scenarios for etcd's data directory, placing it on a relatively slow network-attached disk versus putting it on an incredibly fast RAM disk. Why these two extremes? A network disk represents a common, durable, but potentially high-latency storage option often found in cloud environments. A RAM disk, on the other hand, offers blisteringly fast reads and writes, but is volatile, lose power, and the data is gone unless properly backed up or managed. The researchers wanted to isolate the impact of pure storage speed on the entire system. They didn't stop there. They also recognized that many teams are adopting service meshes like Istio. A service mesh is an infrastructure layer that handles service-to-service communication, offering features like traffic routing, security policies, and observability, separate from the application code. Istio adds components like an ingress gateway to handle incoming traffic and Envoy proxy sidecars, that is, separate proxy containers running alongside each application container within the same pod, to intercept and manage network communication. So the researchers also varied the platform constitution by running experiments both with native Kubernetes networking and with Istio enabled. Their methodology was rigorous. Dealing with the inherent variability and complexity of cloud environments and Kubernetes makes performance testing notoriously difficult. Results can be hard to reproduce. To combat this, they developed and open-sourced their own experiment framework specifically designed for conducting repeatable and reproducible performance experiments in these complex environments. This framework handles setting up the cluster, deploying the system under test, running distributed load generation using Apache JMeter from a separate cluster. Crucially, not running on Kubernetes itself to avoid interference, collecting metrics from various sources like the application, Kubernetes, and infrastructure, and facilitating data analysis. This framework itself is a significant contribution, aiming to tackle the reproducibility crisis often seen in systems research. So what did they find after running thousands of experiments? The results were stark. The performance of etcd, dictated by its storage backend, had a massive, measurable impact on Kubernetes' ability to perform its core orchestration tasks. When etcd was running on the slow network disk, Kubernetes itself became sluggish. This wasn't just a theoretical slowdown, it directly impacted the application. For example, if pods needed to be rescheduled or services updated due to scaling events or failures, which they sometimes induced intentionally in their tests by setting tight memory limits to trigger out-of-memory or OOM kills, a slow etcd meant Kubernetes reacted slowly. This could lead to delays in traffic routing updates, potentially sending requests to pods that were no longer ready or even existed, resulting in errors like 503 bad gateways seen by the load generators, as mentioned in the paper's discussion on probes. Conversely, when etcd ran on the lightning-fast RAM disk, Kubernetes orchestration actions were significantly quicker and more reliable. The entire system felt more responsive, and this translated into better performance and fewer errors for the application deployed on top, even though the application code itself hadn't changed at all. This directly demonstrates that a bottleneck deep within the Kubernetes control plane, specifically its etcd storage I/O, can manifest as application-level performance degradation. Now, what about Istio? As expected, adding Istio introduced its own performance overhead. The paper includes detailed diagrams showing the network traffic flow for both native Kubernetes and Istio deployments. With native Kubernetes networking, using components described in the paper like the Flannel Container Network Interface or CNI provider in VXLAN mode, traffic typically hits a node port service. It then gets routed by kubeproxy, perhaps using IPVS as assumed in the paper, potentially traverses a VXLAN tunnel if the target pod is on another node, and finally reaches the pod via a network bridge and virtual Ethernet pair. It's already several steps. With Istio, you add more hops. Traffic first hits the Istio ingress gateway, which is itself a pod running an Envoy proxy and exposed via a Kubernetes service. The ingress gateway then figures out where to send the request within the mesh based on Istio's rules. It forwards the traffic, potentially across nodes using VXLAN again, to the Envoy sidecar proxy running alongside the target application pod. This sidecar proxy then forwards the request locally, over the network stack, to the actual application container. So you have at least one extra network hop through the ingress gateway and additional processing delay within both the gateway's Envoy proxy and the destination pod's Envoy proxy. The researchers confirmed that this added complexity does indeed impact performance, and critically, it can potentially exacerbate underlying platform issues. If Kubernetes is already struggling because of a slow etcd, the additional load and complexity from Istio might push things over the edge more easily. So what does this all mean for us software engineers building and running applications on Kubernetes? The biggest takeaway is that we absolutely cannot treat the Kubernetes platform as a black box, or just assume it works perfectly under the hood. When we encounter performance problems, especially weird, intermittent ones, the root cause might not be in our code, our database queries, or our immediate dependencies. It could be lurking in the configuration and performance of the Kubernetes control plane itself, like the etcd storage speed highlighted in this paper. This research gives us a concrete area to investigate: the performance of etcd. If you're experiencing unexplained latency or errors under load, particularly during scaling events or updates, checking your etcd deployment configuration is now a prime suspect. What kind of storage is it using? Are there monitoring metrics showing high etcd latency? The paper clearly shows the significant gains possible by ensuring etcd has fast storage. Of course, this immediately brings up a practical question. Should everyone run etcd on a RAM disk? Probably not in most production scenarios without careful consideration. The performance benefit is clear, but RAM disks are volatile. You'd need robust mechanisms for backing up etcd data frequently and reliably, and a plan for restoring it quickly after a node failure. Using high-performance local SSDs for the etcd data directory is often a more practical compromise, offering significantly better performance than network storage while retaining persistence. Some cloud providers offer instances optimized for high I/O performance, which might be suitable for control plane nodes running etcd. The key is being aware of this trade-off and making an informed decision based on your performance needs and tolerance for operational complexity versus the risk of data loss. The paper strongly suggests that the default of using potentially slow network storage might not be adequate for demanding workloads. And what about the Istio overhead? The paper confirms what many in the community already know intuitively. Service meshes add complexity and consume resources, impacting performance. This doesn't mean Istio is bad. It offers powerful capabilities for traffic management, observability, and security that can be invaluable, but it does mean we need to be mindful of the cost. Engineers need to weigh the benefits Istio provides against the measurable performance overhead and the increased resource consumption for the Envoy proxies and control plane components. Rigorous performance testing, perhaps using a framework like the one developed by the researchers, is essential before rolling out a service mesh widely in production, especially under high load. You need to understand the performance delta compared to native Kubernetes networking in your specific environment and workload. Beyond etcd storage, this research opens the door to considering other potential platform-level bottlenecks. What about the performance of the Kubernetes API server itself? Or the scheduler? What about the choice of CNI plugin for pod networking? The paper used Flannel, but how about Calico, Cilium, or others? How do different cloud provider networking implementations interact with Kubernetes? How do resource limits and requests, or even noisy neighbors on the same node, affect things? The paper's focus on etcd is just one specific, impactful example of how the platform matters. The principle is broader. The entire stack, from the application down to the infrastructure configuration, needs to be considered during performance analysis. Does the type of application workload change how much these platform effects matter? The paper doesn't explicitly break down results by workload type like CPU-bound versus I/O-bound. However, we can infer some things. Any application that requires Kubernetes to perform frequent orchestration actions, like applications that scale horizontally very dynamically, perform frequent rolling updates, or rely heavily on service discovery updates, would likely be more sensitive to etcd and control plane performance. An application experiencing frequent pod restarts, perhaps due to the OOM kills the researchers induced to study behavior under extreme conditions, would definitely feel the pain of slow orchestration, as Kubernetes would be slow to remove the dead pod from service endpoints and start a new one. While a purely CPU-bound batch job might be less affected by etcd latency moment to moment, its initial scheduling and any subsequent updates or restarts would still depend on the control plane's responsiveness. Ultimately, this paper serves as a powerful reminder. Building and operating software on complex platforms like Kubernetes requires a holistic view. We need to understand not just our application, but also the behavior and limitations of the environment it runs in. Debugging performance isn't just about profiling application code anymore. It's about understanding the interplay between the application and the platform. The researchers drive this point home by advocating for treating both the application and the platform as the system under test. And crucially, they provide not just the findings, but also an open source framework to help the community conduct these kinds of rigorous, reproducible experiments, which is essential for making real progress in understanding and optimizing these complex systems. So the next time you hit a performance wall in Kubernetes, remember etcd, remember the platform. Dig deeper than just your application logs and metrics. The bottleneck might be hiding in plain sight in the very foundation you're building upon.